Welcome everyone. Today we are going on a journey to map out a building's energy picture. Think of a building like a living, breathing system. Energy and moisture are constantly moving in and out, and all that movement creates a space load that the HVAC system has to manage. By the end of this video, you'll have a clear mental map of where all that energy comes from and where it goes. So, what's our plan? First, we'll zoom in on a single room or a zone to see the big energy picture. Then we'll tackle two super important concepts, sensible versus latent heat, and we'll get a handle on the notation we'll use. After that, we'll take a tour of every single path heat can take to get into or out of a building. And finally, we'll see how all those individual paths, all those individual pieces add up to create the total load that the HVAC system has to handle. By the time we are done, you'll be able to define the two main types of load: sensible, which is all about temperature, and latent, which is all about moisture. You'll also learn to draw your own heat flow schematic for a building, which is a super useful skill. And finally, you'll be able to tell the difference between the decisions you make during the design phase, like picking a window type, and the things that happen once the building is being used, like internal heat gains from people and equipment. These are the kinds of distinctions that make for a great building simulation. Before we get into the details, here's a quick throughout experiment to get your brain working. Imagine you have two identical rooms. They are both at the exact same temperature, but one is a little muggier. It has a higher humidity ratio. Now you introduce the exact same amount of outdoor air into both rooms. Which room will require more cooling or heating, and what's the reason? Things beyond just temperature. Consider how moisture content affects the total energy of the air. Keep your guess in mind, and we'll revisit it once we cover the basics. So let's keep this question in mind. The first step is to define our control volume. Think of the room air as a central hub where we track everything. We use two simple variables to define its state: its temperature, Tc, and its moisture content or humidity ratio, that is Wc. From here, we can see two main types of exchanges. External exchanges happen across the building's boundary, and we are going to point it here. Here. So everything that goes through the system boundary, these dotted lines are the control volume. So these external exchanges can be this heat flowing through the walls, solar energy coming through windows, or outdoor air moving in through ventilation. And internal exchanges. This happens inside the room, like heat from people, or lights, or equipment. The walls and other building mass can even store some of this energy and release it later. So here we have we have to clarify the most important distinction in building loads: sensible versus latent. Sensible load is the part of the load that changes a room's temperature. Think of it as the heat you can sense with your thermometer. Latent load is the part that changes a room's moisture content. This is the energy it takes to add or remove water vapor. We'll use a few symbols to keep everything straight. Tc, Wc, and H these are our zone's temperature and humidity, H for enthalpy, M for an air mass flow rate, and Q for a heat rate. And we use the subindex A to designate outdoor air states, and sometimes an intermediate state X that is helpful for separating sensible and latent loads. Now let's take a closer look at the key pathways heat can take to get in or out our zone. Think of it as a checklist for your building model. First up, the opaque envelope. This is our walls, roofs, and floors. Here heat moves primarily by conduction. But remember, the outside world is more complicated than just air temperature. We account for things like solar absorption and sky radiation with a concept we call solar temperature. Next, we have fenestration or windows. Windows are special because they have two major heat flow paths. First, the conduction, which model with a U value, but more importantly, there is the solar gain, which depends on things like windows orientation, type, and any shading. Finally, we have air exchange. This is the air moving into the building through either ventilation or infiltration. This air carries both heat and moisture, which is why we need to track both sensible and latent loads. When we combine all of this with the heat from people, lights, and equipment, our internal gains, we have a complete picture of all the forces at play. Now for the final step, putting all together. The space load is simple, the sum of all those individual heat flow components we just talked about. It's the total amount of energy, sensible and latent, that the HVAC system has to add or remove to keep the room at a comfortable temperature and humidity. A positive load means the system needs to cool the room, while a negative load means it needs to heat it. This is how we go from understanding the physics of a single component to sizing a mechanical system for an entire building. To wrap up, remember these three key takeaways. First, always distinguish between sensible effects that change temperature and latent effects that change moisture content. Second, every heat transfer path matters. Use a checklist to make sure you've accounted for all the major components: opaque surfaces, window air exchange, and internal gains. And finally, the space load is simple the sum of all those parts. Keep these principles in mind and you'll be well on your way to mastering building simulation. So this is just the beginning. I invite you to continue learning, to go even deeper. Check out these advanced topics. You will explore solar temperature, a clever concept that combines solar and sky effects into a single number to make calculation easier. Or dive into transfer function methods, which help us to understand how buildings' thermal mass creates a time lag in loads. And for even more detail on air, investigate the ventilation load split, which breaks down how outdoor air affects both temperature and moisture. So thanks for watching this video, and I invite you to continue your learning journey. Bye.